Hello, this is Dr. Strickland. In this video, we will investigate conformations of monosubstituted cyclohexanes and 1,3-diaxial interactions. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. All right, so a monosubstituted cyclohexane derivative has one substituent attached to carbon 1 of the cyclohexane ring. And so I'm going to draw a chair conformation. And it takes a while to be able to draw these well. And so if you want to work in pencil for the entire semester, you're welcome to do that. Remember that every intersection that points down has its axial bond going down, and every intersection that's up has its axial bond going up. So they alternate up and then down, up and then down. And I'm going to start my numbering here and just number around the ring. Now the equatorial bonds stick out, kind of like spokes from a wheel. And remember that when you're trying to decide how to draw those equatorial bonds, kind of think about this imaginary line that runs through the middle of my drawing here. All the equatorial bonds to the right of this line are going to point to the right, and all the ones to the left of this line are going to point to the left. And if this axial bond is up, then the equatorial bond is going to angle down a little bit. And if the axial bond is down, then the equatorial will angle up a little bit. All right. I'm just going to put in the hydrogens and that one methyl group. So in the first conformation, I'm going to put the methyl group on the axial bond of carbon 1. So that would be right here. So now remember that this is equatorial, but it's also an up bond. And this is axial, but it's also a down bond. You know that when you flip a ring, everything that's axial becomes equatorial, and everything that's equatorial becomes axial. But the up and down thing doesn't change. So when I flip my chair, this point that's down on the left now goes up, and this is carbon 1. And the point that was going up here for carbon 4 now goes down, and this is carbon 4. And you can fill in your numbers in between. 2, 3, 4, 5, and 6. Okay, so we've still got axial and equatorial bonds. The axials still alternate up and down. The equatorials point out and are angled in their appropriate directions. But CH3 has become equatorial here. And then this hydrogen is now axial. All right, I'm going to put the hydrogens in. In practice, unless I ask you to draw all those bonds to hydrogens, you don't have to. But if it helps you keep your place, then please do. All right, so the methyl was axial and now it's equatorial. The hydrogen was equatorial and now it's axial. But what hasn't changed, this is still the down bond on this carbon, and this is the up bond. Okay, and so that may help you when you're flipping your chair. So we'll consider this the axial conformation and this the equatorial conformation. So let's just call this, we'll just label them like that. Axial conformation, equatorial conformation. All right, and let's let's abbreviate this like this, and then we'll be able to use these labels below. All right. So if we want to determine the relative stabilities of these two chair conformations in solution, then what we need to look at is the 1,3 diaxial interactions. Now, these are another form of steric strain involving axial substituents larger than a hydrogen atom on the same side of a chair conformation. So a chair conformation will be more destabilized by more 1,3 diaxial interactions or by more serious ones. So the only substituent we have that's larger than a hydrogen atom is this methyl group. And this methyl group will have 1,3 diaxial interactions with any axial thing that's on the same side of the ring. So any with whatever is attached to the other axial bonds that are also pointed down, like that. All right, so what we have is a 1,3 diaxial interaction here and one there. So if I just label this like that, we have two 1,3 diaxial interactions, one from here to here, one from there to there. Now, if you look over here, the methyl group is not in an axial position. In fact, nothing in an axial position is larger than a hydrogen. So for the equatorial conformation of this particular compound, there are 0 1,3 diaxial interactions. So which one is more stable? Well, the one with fewer 1,3 diaxial interactions will be more stable. Or you can say the one that has more 1,3 diaxial interactions will be less stable. And like with most things, there will be more molecules in the more stable conformation when you get to equilibrium. We can actually calculate that. This is just a qualitative assessment, but we can do a quantitative assessment. So come on down here. If you know the equilibrium constant for the interconversion of one chair conformation to another, you can calculate the percentages of each of these chair conformations in a solution for any of these compounds. So you'll find these values in table 3.9. And they will be in your table packets when we get to an exam. So for an equilibrium between the axial and the equatorial conformation, so we're talking about monosubstitute cyclohexanes where we've got one substituent on the ring that's not a hydrogen. The equilibrium constant is listed for the conversion with axial on the left and equatorial on the right. That's how we interpret those numbers. So if you want to do the percentages, we're going to do them like you do most percentages, the part over the whole times 100. So if the substituent is a methyl group, the equilibrium constant is 18. And another way of writing that is 18 over 1. And the equilibrium constant is always going to be, for an equilibrium that's written like this, the equatorial concentration on the top and the axial concentration on the bottom. So we can use the 18 to represent the equatorial portion and the 1 to represent the axial portion. So the percent axial will be 1, which represents the axial portion, over the sum of the two of them, 1 plus 18 times 100. And then the equatorial will have the 18 in the numerator and the same sum in the denominator. Oops, sorry, that should be a plus sign. All right, so pause the video and do those two calculations and then come on back. All right, welcome back. So this is 5% and this is 95%. And if you've only got two things represented, the total should be 100. So we can put our percentages up here into the table we were working in before, and now you see we have numerical values that line up with our qualitative predictions as well. Okay, so that is the basic story on these conformations of monosubstituted cyclohexanes. If you have any questions, please send them to me.